Question 5, some more functions. Here we get given in 5.1 the following function. G of x is equal to k to the power x, where k is greater than 0, and y is another function, which is the inverse of g. Okay, and the point 2 and 36 is on g. Let me draw a rough sketch of what's going on here. Okay, the graph G. Here's a point 2 and 36. You can also look at this on your exam paper, your question paper itself. This is G, goes through the point 1 there. And then the other graph, which is the inverse of G, or Y, looks like this. Goes to the x-axis here at 1, and this is your G inverse, or your Y graph. Now the first question they ask specifically about this, 5.1.1, determine the value of k. We know G of x is equal to k to the power x, but we also know that this point, 2 and 36, lies on the graph. So let's just plug that in there. With the y value, we have 36, we've got k to the x value. Yeah, 36 equals k squared, so we'll take the square root of both sides. Square root of 36 equals k, but square root can be positive or negative as a root. So it's plus or minus that. That's plus or minus 6 equals k, but then we see that k has to be greater than 0, so only the positive 6 is your k value. That's it. Oh, 5.1.2. Give the equation of G inverse in the form y equals. Something. Okay, we know that G of x was equal to, k we've calculated to be 6, so G of x was 6 to the power x. So now the inverse of an exponential function, and this is clearly an exponential function, or y equals k to the x, that's an exponential form. So to find the inverse of an exponential function, that's pretty straightforward. If we don't do all the hectic calculations, we can just rewrite it as this. Y equals log of x base 6. So basically just take this whole thing and you bring it down a bit. Instead of 6 to the power x, we now have x base 6 for a logarithm. And that's your answer. You could also work it out the traditional way of swapping your x and your y around and then solving for y. Actually, let's go through it just in case they do ask it. So the alternative method, which takes a bit longer and it won't be worth only 2 marks. Let's see how that works. So we start off with our initial equation as y equals 6 to the power x, and then to find the inverse, we swap x and y around. So x equals 6 to the power y, and now we want to solve for y. Now you need to know the rules of logarithms for this, how you get from this into a logarithmic form. Or you can just say log of both sides. I think that's actually an easier way to do this, and you don't have to memorize any formulas. So we'll just say log of x equals log of the right hand side as well. What do we know about log of something to a power? We can move that power to the front of the log. So let's do that. Log of x equals y log 6. Now we want y by itself, so we'll divide both sides by log 6. So we have log x divided by log 6 equals y. And log x divided by log 6 is exactly log x base 6, which equals y. So this is the alternative, slightly longer method to get to that same answer. And this is a safe way because in this way you know what you're doing, where that way you've probably just memorized how to get there. But it is quicker. So whichever way you prefer is fine. Next question, 5.1.3, states for which values of x is the inverse of x less than or equal to 0. Let's have a look again at what that graph looks like. G inverse looks like this. Goes through 1 there, and it's asymptotic to the y-axis. So it never touches the y-axis. Now asking us, where is this graph less than 0? Where is it below the x-axis? Which is the same as saying, where's the y value, which is the name of the graph? Where is that below 0? And we can see it's clearly this part here, this part. Now for which x values is that true? So if we take an x value greater than 1, we see the graph is bigger than 0. At 1, it's equal to 0. Less than 1, less than the x value of 1, the graph is below the x-axis, but not at 0, or not anything below 0. So only between 0 and 1. Is that true? So we'll just say that for all the x values greater than 0, but less than or equal to 1. So it's less than or equal to 0. And that's your answer. Next question would be 5.1.4. 5.1.4. And they ask us, write down the domain of H if H is equal to G inverse of, rewrite that question. 5.1.4, they say H of X is equal to the inverse of X minus 3. Now they want the domain of H. Let's look at what the domain initially was of G, of just the inverse of G. Domain means all x values for which this graph exists, all possible inputs. So which x values does it cover? Well, it doesn't touch the y-axis, so it doesn't touch x equals 0, and it's not on the left-hand side of it at all. But on the right-hand side, it continues indefinitely. So it's all x values greater than 0. That's the initial domain for G. Now for H, we'll see it has G of x minus 3. So this little negative 3 just means you shift the whole graph 3 units to the right. So it would look something like this. So the whole graph shift each point shifts 3 units to the right. So the domain now, even the asymptote here would shift 3 units to the right, from 0 to 3. So this is the asymptote of the new graph. So all values greater than 3 we see is now part of the domain. So the domain of h of x is x is greater than 3. That's the domain. So if you see x minus or x plus something inside of a bracket, how that changes the graph, it shifts it whatever n units to the right or the left. For a negative it shifts it to the right, and for a positive it shifts it to the left. Whereas if we had something added onto the end here, if they asked what is the domain of, or how does this change the graph, g of x, and then they said minus 3 there, that would mean shift the whole graph 3 units downwards. But in here, inside the bracket, shift it 3 units to the right. Okay, 5.2. 5.2.1, as I sketch the graph of the inverse of y equals 1. Okay, first of all, let's draw the graph of y equals 1 to see what that looks like. Okay, if y is equal to 1 everywhere, then obviously the graph looks like this. It's just a horizontal line that everywhere y is equal to 1 on that line. Now an inverse, the definition of an inverse, you can see it a couple of ways. We know to find an inverse we have to swap x and y around, but swapping them around just means you're turning one into the other, which means they are equal. So an inverse is actually geometrically a reflection of the one graph in the line y equals x. So you can just imagine, what does the reflection of this graph look like? Well, it would look like this, of course. If this line was a mirror of this value being 1. Okay, so you could also see it as wherever there was a y, you now put an x, wherever there was an x, you put a y. That's another simple way of thinking about it. What does this graph look like? This equation of this graph, everywhere along this graph, x is equal to 1. So the answer is x equals 1 is the graph of that. But you could also see if you said let y equal x and let x equal y becomes x, there was no x, so now there's no y. And that's a sketch of the inverse. So y equals 1, the inverse of y equals 1 is x equals 1, and this is the sketch for that. 5.2.2. Is the inverse of y equals 1 a function? Okay, the inverse of y equals 1 is this x equals 1 line. So is this line a function? What is the definition of a function? Well, let's think a bit about that. Definition of a function is that each, for all x values, has unique y value. Or every input, and x is an input. So for each input or for each x value, there is only one or a unique output or y value. Let's see in this case. In this case we have an x value of 1, for instance. Is there only one specific y value for it? No. It has lots of different y values, infinitely many different y values. So no, it is not a function. Why? We can give an example. For x equals 1, any y value, or indefinitely or infinitely many outputs or many y values. That's it. Okay, that's it for question 5.